Hello, my name is Cristian Alejandro Garcia Mendoza, and beside me is my colleague Jose Pablo Sedano. We're going to introduce you to the two projects that we worked on here in our internship at Chalmers. The first project is the migration from ROS to ROS2 of a system that involves navigation, perception, and decision making applied into a robot named Tiago from Power Robotics. And we also worked in a project for the integration of navigation competence with causal models.
As my colleague says, we're gonna work in the migration from ROS 1 to ROS 2. The project was in the Tiago was made on ROS 1, and our task is migrate this architecture to ROS 2. And our second project is to extract the data from the Tiago to visualize the trajectory with the navigation competence with causal models. So our first project was the perception and decision making with YOLO and ChatGPT integration for intelligent robot navigation. This is the title of the master thesis we worked on, and we had to migrate this from ROS to ROS2. And so the first thing we got to get the base of this project, which was ROS. We needed to learn how to use ROS because we knew ROS2, but it's not quite the same. And also we needed to understand and know how to use Docker because the simulation of the Tiago works with Docker. And also we needed to comprehend what the master thesis, which is the fundament, which is the base. So we needed to comprehend these nodes that are the base of the project.
Okay, so the new system looks like this. So the robot has not the robot has not been updated with the new ROS2 image right now. So the robot is running on a system from PAL Robotics called PAL Gallium and also the ROS Noetic environment. And we had to migrate this into ROS Foxy because it is the only ROS image that is bridgeable with the ROS Noetic environment. So to the left, we begin with Tiago as a node. It has several nodes inside of it, but we represented it just as a node because we didn't get to interact with the inside of that system. This system publishes a lot of topics in which we find the Joy-Con priority, the joystick priority, the navigation velocity, the robot's pose, and other topics that we use for the system. Then we go into the Tiago Ross bridge. This is the first node that we had to forcibly put into this system because the communication speed was really slow and we had to enhance this communication speed. And we also had lots of data loss. For example, when we got the image, it was very lagged and we really could not get a more fluent image of the robot. So we had to put this node. And then we also have in the ROS environment, we have down to the bottom a creating instance node, which also communicates directly with the robot and gets the map, the robot's pose, and gets also some topics from the object detection node to then publish into the ROS1 bridge node. This is a ROS2 node from the ROS1 bridge package. This enables a communication between ROS2 Foxy and ROS Noetic. And then this ROS1 bridge node publishes lots of information, receives and publishes lots of information from the ROS Noetic to the ROS Foxy environments and vice versa. So we have 5 nodes in there and that are basically the perception and decision-making nodes. And then we flow back into the ROS1 bridge and we go into the ROS2 Tiago bridge down to the bottom left. And this node is basically the node that gets information from ROS2 and publishes it back to Tiago to make it actually move or behave, since we didn't have custom messages for we were not able to bridge custom messages from the Tiago to the ROS2 environment. We had to build those messages in the ROS2 environment, then also in the ROS Noetic environment, bridge them and make the ROS noetic publish them back into Tiago so that we have this compatibility with custom messages and also with the speed, communication speed, so that the robot Tiago would move when we desired that it moved. Now, for the perception and decision-making system that is all the way to the right, I'm going to let my colleague explain two of the nodes that he was working on.
Yeah, so everything begins with the object detection node. It implements a YOLO model to detect objects. We have the input of our raw image and also the depth image from the RGBD camera. And with that, we process this data and we publish the image with the detected objects, and also we publish the detection results with that contains what is the object detected and also the depth information of that object. And that information from the detection results, it goes into the decision-making node and the human speed node. So in the human speed node, we got the robot pose, and also if the detection of YOLO is a human, also can detect the human speed.
Then we have other two nodes that are the wall detection and the decision-making node. I'll begin with the wall detection. This node is described to three topics, which are the robot's pose, the scan 2, and map 2. These have the two because those are the topics that were bridged. So to not mess with existing topics from Tiago to the new topics that we could work with in a more efficient way. So the scan topic basically gives us the information the robot obtains from the laser sensor, and the map is basically the initial map we get from the environment, so that the robot knows where it is navigating. It doesn't know the room, though it knows the shape of where it is at. Based on this information, the wall detection node analyzes the occupancy grid map that the map has and also the scan detections that it gets from the sensor. And basically, it differentiates objects and walls and obtains the distance that the robot has between these two and publishes them into the decision-making node. And this decision-making node, based on that information, based on the information it gets from the object detection node, the human speed node, and also the creating instances node. So basically, the creating instances node, I have to explain it also. It works on a package that is named NoRob, which involves knowledge from a robot based on ontologies and another language of programming, which is Prolog. And based on these ontologies, it receives the object that the system is detecting, and with the aid of OpenAI and the NoRob, it outputs a room in which, it infers a room in which the robot is located, and then it goes also into the decision-making node. And then this node this node based on the room, the robot speed, the objects around it, the human speed, and all that information takes decisions, as its name says. But the behavior is interesting. We have 4 scenarios in here. The first scenario is where it doesn't recognize where it is at. It has a certain design behavior to react to the environment. It also reacts to when it is located in the laboratory. It reacts when it is located in a living room and also in a hallway. This behaviors change basically the speed that the robot has, which means, like, for example, when it's in the hallway, it can go at normal speed. And when it sees a human, it can go slowly when the human starts getting close to it. Or maybe when it is in the lab, when it sees a human, it within 2 meters, it stops. And also something that differentiates behavior from just moving or stopping. It's that it also talks and outputs the reason behind its behavior. So when it sees a human within 2 meters, the robot visually goes stopping. Human detected the 76% within 2 meters, or a wall detected within 1 meter, slowing down. It depends on the situation, but basically, these are the four outputs that we get from the decision making node. And yeah, those decisions in the of speaking and the velocity go back to the Rosman bridge, which go to the Ross to Tiago bridge, and then go to the Tiago robot, so that the behavior is applied and we can actually see uh, the behavior, the robot's behavior being manipulated by us. So the following video is us experimenting with navigation. As you can see, the robot tends to do a lot of spinning around, and it's itself trying to find itself in the environment and recognize the map. However, in this example video, the robot didn't find its location, and it didn't find its way to the goal. So from there, we realized that there are some improvements needed in the actual path planning of the robot to the goal, and that's what leads into our second project.
Okay, so knowing that it exists room for improvement, we gotta work as assistants on a PhD project called Navigation Competence with Causal Models as classifiers. So the main goal of this project is to improve the navigant's competence through this model. So what they asked us to do was to make rollbacks and create a visualization of the Tiago path and the cluster method to make sure it's competent. And we decoded uh, a lot of data, and between this data, it concerns us the Euclidean distance, the angles, the goal, the map in two ways. I'm gonna get that in later. It's the global and the local map. And we get the transformation of the post through global to local, and also we need the planned path. And all of these data were decoded into a CSV format for a easier and better manipulation of that data. So that was the thing I was telling to you, the, the difference between the global and the local map. For the visualization of the path, we need the local one because for plotting purposes, the global doesn't work out, and the local uses the Tiago as the center of the map, so we can't use it in a better way. And in this code, that's the way we extracted the Euclidean distance through the robot poses. We stripped down the position in X and the position in Y, and with that we got the Euclidean distance, and also we got the deltas of the position, and with that we calculated the angle in radians of that robot through the angle of the robot and the goal.
We also had to get this angle right in a local way, since we also had to get the angle from the robot to the goal in the robot's perspective. So what we did was basically get the robot's orientation, and we got it. We made it into an angle in radians that we could work with, and we subtracted this robot's angle from the angle to the goal in the global setting, in the global frame. So that's how we got the angle, the difference of those angles. And this also had to be done with the paths. So we also had to get the Euclidean distance from each point in the path, and also the angle from each point to the goal, to also feed the causal model and make it comparable for make it comparable, the causal model's behavior and also what the robot thinks it'll do.
So yeah, as I said earlier, the model worked with an interpolation extrapolation method. So we had a problem. All these, the input were the Euclidean distance and the orientation of the robot, and these were extrapolated. So we had a problem. We had less maps to plot than data. So what we had to do was to extrapolate as well the map. So this is a nice visualization of how it worked. This is the CSV file we extracted or decoded. So we can see the occupancy map, or in a simpler way, which cells are occupied. And then we transform it into a map. We can see a trajectory of the robot. And this is, we can see it's only 11 frames of map, but with the extrapolation, we can get the same as the position of the new extrapolated points, so we can match the visualization.
So the path format had to go through several changes due to plotting circumstances. First, we used to have like all the planned paths data in individual cells, and the problem with this is that we cannot differentiate from one path to another. You could do it visually, but it would take a indefinite amount of time to be able to do that. So in exchange, what we did was put these paths into arrays of positions and orientations that we could manipulate easier. And the good thing about this is that we had the future path in a better organized way. We could differentiate the complete path, the future path, and each one of the paths at each time step. We could differentiate all of them and have them plotted at the respective time that they needed to. This is what I meant when we cannot differentiate the path. So this is the past plotting of the robots. So to the top left corner, we can see only one path that is basically the real path that the robot followed and its future path. It is quite sped up, so that's why it goes really quick. But yeah, we could not fit that into the causal model. We needed to fit each individual path, and as you can see, there are lots of paths in the plottings, and this is basically the robot following. It sort of following them. It follows like something in the middle, but yeah, this is this is what I mean when I say that we cannot get each individual path plotted, but all of them at the same time. That's why we got into the next step. The actual plotting. So this is global plotting, which I've had to remind you that the causal model uses local information instead of global. So we had 5 different scenarios in which we prepared the robot to reach a goal with one obstacle in the middle, with a sudden obstacle, with a human just popping out of nowhere, with some obstacles in between, and just a straight line. So as you can see, there are there's several information in each graph, and basically, as we can see, the black dots, the black line is the robot's path that it has followed. Then we have some arrows which represent the orientation of the complete path and the orientation of the future path, the trimmed path. And yeah, some lines that basically represent the positions that each path follows along the way. And yeah, this is what we got from the actual plotting.
So, okay, now we have our global mapping, our global trajectory visualization. But now we gotta transform these coordinates into a local way. We have the map, but we don't have the coordinates. So with the data transformation, or TF, it's a library and topics in ROS. It helps us to transform these coordinates. You can see an example. This is the local, and we transform it through these coordinates. And now we have, and this is the code how we did it. And in that way, we have our coordinates in a local way. We can see through this how it was transformed. And now we got this output, and we got the same visualizations.
Yeah, we got these visualizations now that are basically the local plotting. We can see 2 goals in here. We can see a red dot and also a blue dot in each one of the graphs. The red dot is basically the complete path last position, which basically represents the goal, but it's not necessarily the goal. And we also have that's a blue dot, and the red dot is what we computed as the goal with the Euclidean distances and angles that we got. So this is a more accurate way of representing the goal, and this is also the exact information that we will feed into the causal model to get our new proposal for a new path to follow. So this is the behavior that we got from the clustering and the robot. So you can see it is with the local map implemented. Could you reproduce that again, please? So we can see how the robot follows the green square. The green square is the goal, and we have lots of arrows, which are the orientation of the path at each given point, of the complete path for the orange arrows, the future path for the cyan arrows. We have also the positions plotted in a blue line and in another red trimmed line, stripped line. And the pink arrow is basically the cluster's behavior. There's still some work to do into the implementation of the clustering, since it is not following the behavior it's desired. But this is the results until now. And thanks for watching.